Good morning, everyone, and welcome to our webinar, Integrated Systems Planning. Thank you for joining us today. My name's David Farmer. I'm a senior consultant with Advanced Energy, and I'll be your moderator for today's discussion. Today's webinar is part of Advanced Energy's Exploring North Carolina's Clean Energy Transition webinar series, formerly known as Exploring North Carolina's Smart Grid. This is the second of three webinars to be hosted this year as part of the program and the 19th since we began the series. Advanced Energy is a nonprofit energy firm founded in 1980 by the North Carolina Utilities Commission that provides research, testing, training, consulting, and program design. Our members are Duke Energy, North Carolina's electric cooperatives, and Dominion Energy. Since 2017, our team of technical and training staff have collaborated on this webinar series to provide stakeholders with a convenient option to learn how smart grid and the transition to clean energy is changing North Carolina's future. Before we go into today's presentations, I'd like to cover a few housekeeping items. We'll be using the Microsoft Teams webinar platform, so if any point you want to interact with us, please submit your questions or comments by using the Q&A button on the top of your screen. The chat feature has been disabled for all participants. We'll respond to as many of your questions as we can at the end of the program during our Q&A session. The webinar is also being recorded and will be available on the ncenergytransition.org website. Following today's webinar, we'll send a follow-up email with a link to the recording, and you can review any of our past webinars on this site. Finally, at the end of today's webinar, there'll be a participant satisfaction survey. We welcome your feedback, so please take a few minutes to complete the survey to help us improve our future webinars. First, let's take a quick safety briefing. Wherever you are, please be sure you're in a safe place to listen, view, and participate in this webinar. If you're driving, please find a safe place to pull over. Take a moment to be aware of your surroundings and remove any tripping hazards should you need to move around or evacuate. Know your exits and your evacuation route, and most importantly, take care of yourself and others, and this includes any COVID-19 precautions applicable to your location. Today's webinar has three main purposes. Review the integrated resource planning requirements for North Carolina's regulated utilities, to gain an understanding of the difference between traditional capacity planning and integrated distribution systems planning, and finally, to explore how the utility planning process is evolving. Today, we're honored to have two invited guest speakers who are leading the integrated systems planning efforts at their respective utilities. First, we'll hear from Gus Johnson of Dominion Energy. Mr. Johnson is the Director of the Distribution Grid Planning and Asset Management for Dominion Energy, Virginia. In this role, he leads organizations responsible for capacity planning, reliability, vegetation management, standards, GIS and asset management systems, and preventive maintenance programs. Gus is a licensed professional engineer in Virginia. He received his bachelor's degree in electrical engineering from the University of Delaware and an MBA from Virginia Commonwealth University. Next, we'll hear from Mike Ribb of Duke Energy. Mr. Ribb serves as Director of Integrated Optimization, part of the Integrated System and Operations Planning team. He currently leads a cross-functional team that is developing and testing new collaborative processes across this company's planning disciplines. That includes generation, transmission, distribution, distributed resources, grid solutions, and customer programs to integrate planning results and optimize resource decisions. Mike's background is in engineering, program, and project management, and he's a licensed engineer in Florida. We're grateful to be joined by both of our panelists today. Before we transition to Gus's presentation, let's take a quick poll of the audience. You should see a pop-up window with the question and 5 possible answers, and you'll also see it in the chat. Depending on your screen resolution, you may need to use a scroll bar in the window to see all the selections. The question is, on a scale from 1 to 5, with 1 being not at all familiar and 5 being expert, how familiar are you with the concept of integrated systems planning? We'll pause a few moments while people make their selections. Okay, it looks like most people have already voted. So looks like number 3, which is kind of a neutral response there, but also number 2 and number 4 are pretty well represented too. Okay, thank you very much for taking that poll. That gives us an idea of the audience. And now I'll happy to turn the presentation over to Gus Johnson of Dominion Energy. Gus?
Morning, David. Can you hear me okay?
Yes, we hear you.
Awesome. All right, good morning, everyone. As David said, my name is Gus Johnson. I'm Director of Electric Distribution, Grid Planning, and Asset Management for Dominion Energy Virginia. And today I'm going to give you an overview of what we're doing with integrated distribution planning. Dominion is really at the inception of its integrated distribution planning efforts. So today I'll talk about what integrated distribution planning is versus traditional capacity planning. We'll talk about some of the inputs to our integrated distribution planning. And then I'm also going to talk to you about really the ecosystem of things that plug into integrated distribution planning. As you'll see as I get to that slide, integrated distribution planning is a pretty big and complex thing, which touches a number of systems, but it's really the direction that we as utilities need to be moving into, in my opinion, to make sure that we are ready and the system is ready for all the things that are coming along from a distributed energy resources standpoint, be it solar or wind or electric vehicles or the electric school buses that Dominion has been working on for the last couple of years now, to stationary energy storage, to thermostats, to the whole gambit of things that is included in the definition of DER, per FERC. So let's start with traditional capacity planning versus integrated distribution planning. So from a traditional capacity planning standpoint, that typically deals with one-way power flows. So what do I mean by that? One-way power flows is our typical and traditional view of the electric distribution grid. You have very large generators, be it nuclear or coal or gas, or even a large hydro plant that we have in our service territory that are pretty much centralized. So it's centralized generation, it hooks into our transmission system. The transmission system transports that electricity over long distances. It is then stepped down to a distribution level, transported a little bit more, stepped down again, and then delivered to all of our customers, be they residential, commercial, industrial, et cetera. So it's really one way. It comes from the top, from a large generator all the way down to our customers. Typically, the way that we analyze our distribution system is a seasonal peak load analysis. So what does that mean? We look at our worst case or our peak loading in the summer, and then we also look at our worst case or peak loading in the winter, and we basically plan our system based on worst case scenarios, if you will. So how bad will it be? At its worst, will we have enough capacity to make sure that we are planning the system and our system is built out to accommodate and make sure that all of our customers stay with their lights on? It is a manual analysis, so not completely manual in terms of flipping switches and plugging things in here or there, but there's very little automation involved here. I mean, we do some case building from an automated standpoint, but a lot of the analysis that's done by the planners in my organization is very looking at their case, plugging in their assumptions manually, pulling in their load forecast. There's a lot of steps that are involved in it that would be considered, very manual. And then our planning horizon is pretty short at this point. Typically, we're planning the system a year or two ahead of time. We're taking some longer term views, but we really aren't equipped right now to plan the system for the 5, 10-year horizon, with any high degree of accuracy. So that's kind of our current state in our traditional capacity analysis. Integrated distribution planning, or advanced distribution planning, as it's sometimes called, takes it to a different level, involves a little bit more granularity, both from a temporal perspective and a spatial perspective. So it's smaller slices of time, and we're looking at it not just at its peaks, and then we're also fully building out and looking all the way across the system to make sure that we can see everything. So we talked about one-way power flows, and in integrated distribution planning, we're looking at two-way power flows. So that's where you get into your integration of distributed energy resources, your rooftop solar, your utility grade solar and wind, batteries, be they residential batteries or smaller batteries in substations like the pilots that we're running right now, or I mentioned our electric school buses earlier. We were utilizing them in a vehicle to grid capacity to aggregate them and provide a resource to the electric distribution system. So now, instead of having your generators at a high level going through the transmission system and down through the distribution system before it hits the customers, now you can have that, but you can also have resources that are feeding power back on through the distribution system, and in some cases back feeding onto the transmission system. So that's what we mean by two-way power flows. Really, you could have energy coming from any direction, hence the term distributed energy resource. It is distributed across the entire power grid. Also, in integrated distribution planning, we're going to do multi-scenario analysis. So that looks not only at the worst cases, but things coming from different directions. We're also looking at the availability of the system as well. So in your seasonal peak load analysis, you assume that there are no outages, you're not taking anything out for construction. Basically, your system is completely intact. In a multi-scenario analysis, we're looking at how the system will look over the course of the year, including all of the outages that we may need to further build out the system, to further prepare it for the integration of everything that's coming, all the DERs that I mentioned, and the electric vehicles that we know are coming to both the Virginia and North Carolina service territories, as well as all the other territories across the United States. We're also looking to do much more automation, make it streamline things, make it more easier for our grid planner. So there's some of the manual processes that they have to do now will now be automated, and we can utilize our computing power to really analyze things a little bit quicker. And lastly, we'll leverage strategic and probabilistic planning to assess potential impacts of evolving policy. So that's a lot of words. What does that mean? There's a lot of policy coming around. In Virginia, we were dealing with things like the Virginia Clean Economy Act, which requires us to have 16.1 gigawatts of solar, onshore solar and wind by 2035, 2.7 gigawatts of energy storage by 2035. That's a policy thing. We're also looking at an influx of EVs due to policy. So as these things come up and we have changing and evolving policy that affects the distribution system, we also need to make sure that we're utilizing strategies so that we can plan and build the system out to accommodate these things. So key elements of integrated distribution planning. So the first thing I want to talk about here is data availability and integrity. So with more sophisticated analysis comes the requirement for more data. But not only do you have to have more data, it has to be available, and it also needs to be dependable, and there needs to be integrity associated with that. So to support that, as part of our grid modernization efforts, we are deploying things like AMI, which is advanced metering infrastructure, or smart meters, as most folks are used to thinking about them. We're also doing things like intelligent grid devices. So this could be anything from a smart recloser on a distribution line to line sensors, to things like power quality monitors, all things that will plug into the system and give us more feel on the system. Think of it like the fingers on your hand. You're able to touch and see and smell and hear things, and we know a little bit more about how the system is moving from a day in, day out basis. Synchro phasers are also a part of that as well. For anyone who's not familiar with synchro phasers, that's basically high resolution information, looking at power flows either on the transmission or the distribution system, and it can be as sophisticated as 30 samples per cycle. It allows you to see a lot of stuff on your system. IC 61850 is another thing that we're deploying in substations to really digitize our information further than it is today and provide more granular, more accurate information in our substations. So that's the data availability and integrity part. So you got to have good information going into your planning process in order to have good results. It's the old adage, garbage in is garbage out. So you want to have clean information in to provide a good analysis. Second leg of this here is forecasting. So we're looking at some advanced forecasting tools, both from a load and from a distributed energy resources perspective. So we need to do things to increase our ability and advance our forecasting from a load perspective, but we also need to know what the distributed energy resources on our systems are doing. Again, this is the rooftop solar and forecasting related to that. We're doing forecasting related to electric vehicles, forecasting related to everything that will interact with and plug into our system. So that is a very, very large part of integrated distribution planning. Your data availability folds into that as well because it needs that to do the forecasting. And we talked a little bit about analysis in the last slide. That is granular time series distribution system modeling and analysis. So that is smaller slices. So instead of doing a peak analysis, we're looking at it multiple times over the course of the year, and there's several different ways to accomplish that. And we're also doing more spatial, a deeper dive into our system to make sure that we really understand how each leg of our system is operating and performing analyses on that. And lastly, distributed energy resources. So I've talked a lot about distributed energy resources. It's all the things that I talked about, but it's also utilizing a distributed energy resource as what's referred to as a non-wires alternative. And for those who are unfamiliar with that, traditional alternatives or traditional solutions to solve grid problems are things like transformers and larger conductor and voltage regulators. You have some capabilities with distributed energy resources, and the utilization of them as a non-wires alternative says, can we take a distributed energy resource and use it in lieu of or in conjunction with your traditional wire solution to kind of have a hybrid or an alternative solution to solve grid problems and utilizing those capabilities. We're also talking about the integration of DER interconnection and hosting capacity analysis and folding that into our distribution planning process. So right now we have 3 different hosting capacity analyses out on our website if you go and look at dominionenergy.com. There is a utility scale hosting capacity analysis and a map that is produced there. There is a behind the meter or residential hosting capacity analysis that is done. And then there is an electric vehicle hosting capacity, a smaller scale hosting capacity analysis that we have produced out there. And basically what that tells you is that if you look at any part of the grid, it tells you basically the availability and the capacity of the grid to be able to take in large scale distributed energy resources, small scale distributed energy resources, and also the availability of the grid to take on electric vehicles and the load profile that is produced from that. Another consideration for us, as we go into our integrated distribution planning, is that not all solutions to distribution problems will be owned by the utility. There needs to be some room and some accommodation for customer provided solutions or third-party owned solutions as well, in whatever form they may come in. And that's all the forms of DER that I spoke about in the previous slide. FERC Order 2222 and what comes along with that will be a very large part of that consideration and how it interfaces with the grid. So let's talk about the ecosystem of distributed distribution planning. So I mentioned earlier that there are a lot of things that plug into integrated distribution planning, a lot of stuff that we need to make it work. So I've already talked through a few of them, but let's go through the gambit here. So we have our geographic information system. Think of this as like our Google Maps for the utility. This is a map that shows all of our information, all of our assets, how our system is connected. That is an input to our integrated distribution planning process. We also recently got approved a voltage optimization program that looks at optimizing our voltage across the system to make sure that we are delivering value for our customers while also keeping them within filing of what we are mandated to provide to our customers from a terms and conditions perspective. There's our Advanced Distribution Management System, or our ADMS. This is the system that our operators use to operate the distribution system. Traditionally, it has just been used to view flows on the system, look at the status of devices, reclosers, breakers, et cetera, to see whether they're open and closed. You do switching out of it, but there are also many advanced applications that can be plugged into it, including the advanced power flow analysis, some outage management things, which is the next bullet there. So there is advanced functionality, and that information as well needs to feed into the integrated distribution planning process. There's also a distributed energy management system, or DERMS, which was recently approved as part of our grid modernization effort. This system monitors all our DERs, optimizes them, optimizes our demand response program, and is really the house for all things distributed energy resources. So that needs to be a part of our planning process, as I mentioned earlier. There's an enterprise asset and work management system, which manages all of our assets so that we understand the health of those assets, what inspections have been done, what we expect to see from these assets, how they're performing, the loading on these systems, and then our work management, which ties into maintenance cycles, both preventative and reactive maintenance, and provides an input to how our system is planned. Advanced forecasting we talked through already. Our customer information system, information on our customers, their particular loading from our metering system, which is AMI in our next section there, and how all that information in terms of what programs they're a part of. If you're a rooftop solar owner or you're a net metering customer, that information goes into our planning process as well. So as you can see, integrated distribution planning is a much larger, more comprehensive effort than the way utilities have traditionally planned their system. Hence, all of the inputs from various systems and the focus on data integrity and data quality. These are all the things that we believe are needed so that we can sufficiently plan the system moving forward. So with that, I will hand it off to Mike from Duke Energy.
Yes, thank you very much, Gus. And so, Mike, you can go ahead and take it away.
All right, thank you very much. Really appreciate that. Good information, and a lot of what Gus has shared really does resonate with us and apply to what we're doing as well. I really wanted to just start at a very high level and suggest that we have some really complex challenges we're trying to address. And it's, we're going to show kind of how we're addressing that across the enterprise in the discussion today. We're addressing increasing levels of distributed energy on our systems, as Gus suggested, and also the rapid transition towards clean energy resources. So one of the challenges that we have is that there's a need to balance the urgency to move more quickly, which is self-evident in all the work we do in the industry, with what I consider the complex realities of executing these transitions and maintaining the stability and reliability of the electric system. So we're really trying to balance those and be able to understand things. But our planning methods, which may have evolved over decades, are addressing changes that are happening very fast. So we do our best to focus on what's most important and to try to adapt our process in the best way we can, to leading us towards our priorities in the future. ISOP helps our company meet these challenges with a focus on collaboration and on modernizing the system planning tools and processes used by our generation, transmission, and distribution planning teams. So I'd like to provide a quick overview of how we're approaching that at Duke Energy. I realize that we've probably reviewed versions of this before, but let me just take a moment to share again for folks who might not have seen this, what we're working on and how we're approaching it. As we're showing here, we still have distinct planning groups addressing bulk system generation, addressing and transmission, and the distribution systems. And each of these segments develops asset plans each year to address the path forward for each of these business units. So ISOP is working closely with these teams, developing a highly collaborative environment to help address integration of distributed resources, including generation and storage, and also to adapt to customer-sided generation and flexible load and demand response programs that really bridge across all of these planning segments. So while many of these resources may be connected to the distribution system, the effect is really felt across distribution, transmission, and generation, and ISOP is working on being able to make sure that all of those planning disciplines can see the resources and that we have an idea how they are integrated and valued. So as we go forward, our integrated plans are reflected in the IRP and in the carbon plan, which is a traditional output from the generation or resource planning function. But they are going to be more informed by the bulk system contributions of these new distributed resources in the future. As well, our T&D grid improvement plans like GIP and the multi-year rate plan will also be including more cross-functional benefits analysis for the contribution of distributed resources and customer programs that can impact at multiple levels. So, and to go through this, I'd like to share some examples of how the new tools and processes we've developed for each of these areas are unfolding. I'm addressing some of what I call the initial ISOP objectives to share things that we started working on earlier in the process and that we likely have put into practice already. And I'd also say that this process, just like the industry itself, is really a journey of discovery and experimentation. So as we walk through each of these areas, I'd like to also mention some of the additional ideas we're exploring that may be in mid to or early to mid stage development at this point. So we may not know exactly how they're going to be integrated yet, but they're interesting and they may be material as we address these challenges for the future. So let me start with generation and integrated resource planning. So our first objectives in generation resource planning were to transition to the Encompass modeling tools, and this happened a few years ago. These tools from Anchor Power Solutions have been an important platform for us to help really examine our pathways for decarbonization and also to incorporate more detailed ancillary requirements forecasting into our model. And just for a brief moment, I'll suggest that ancillary requirements are really the flexibility that the system has to adapt to changing conditions. So as you have higher levels of variable resources like solar or perhaps in the future wind, you need more tools on the system to help maintain stable output. So we're trying to address those dynamics in our planning tools. And this Encompass suite of tools has really helped us deal with these more complex clean energy portfolios. Another tool that was developed and has been shared publicly is what I'm showing here, the portfolio screening tool. And this is a tool that was developed as a simplistic way for the users, whether it be utility planners or other folks who are interested, to make changes to the resource mix to, say, retire certain types of generation, replace them with other types of generation, and just get a visual representation of how these portfolios might perform under challenging conditions. We have scenarios in there for a challenging winter week, challenging summer week, and also shoulder months where there can also be extreme challenges, including what we think of as low load conditions, where our load may drop so low and our solar output may be so significant that we are faced with trying to get a lot of our generation literally out of the way. So there's a lot of complexity that goes into how you plan a system like the one that we envision in the future. And this tool provides some interesting snapshots into that. So while this isn't a substitute for more robust integrated planning analysis, it does provide some intuitive screening results that help you understand the resource integration challenges we're going to have ahead of us. So later in the slides that'll be distributed, there's a link if you're interested and you'd like to go look at this. So I think, I've covered most of our initial objectives, and the things that I've described are systems that we have in service now. I mentioned the clean energy scenario portfolios as a very important part of integrated resource planning, and I think the work we've done in the carbon plan is evidence of how far we've come in being able to look at many different futures and deciding which ones we need to focus on. Looking ahead at some of the next stage tools, one is advanced data visualization tools, which is critical to be able to go out into some future year and try to see what the models are telling you about what's happening. How are batteries working? How do they interact with pump storage? How much solar is being curtailed? Those kind of things become critically important when the system changes to the significant extent that we anticipate that it will. We're also developing what we call proxy values to try to measure the production cost benefits that we see that batteries may be able to provide in performing some of these services, ancillary services and energy arbitrage. So we're trying to use the tools to develop approximate methods to value those contributions. And I'm talking about this as a next stage objective because it is a work in progress. But for those who are working on working in or around the multi-year rate plan, you'll see that some of these values are being used. Some of the early preliminary values are being used to start supporting our planning assessments. We are going to continue to look at more robust dynamic system reliability requirements because the system is changing so dramatically. We need a much more granular measurement of system reliability and the vulnerabilities we have. We're also looking at advanced technology on the generation side and how it impacts the system. That could be anything from utilizing hydrogen and hydrogen storage, small modular reactors, and even we're looking at some electrification options at the generation plants themselves. So a lot of different things happening, a lot of things that we're looking at. ISOP is not primary on most of those because there are folks that are doing that full time, but we are helping assist them and also helping make sure the modeling keeps up and that we're able to value those capabilities. I'm going to jump to transmission next. In transmission, our initial focus areas were number one, and this is really across transmission and distribution, is to work on a much more robust and reliable grid system data model. I think Gus really explained this well, and how important it is to have reliable data with integrity, and trying to get all your data systems aligned, because these tools might have been used in different places in the company. So we've done a lot of work on pulling those data systems together and working on the data integrity, as Gus also discussed. We've also done more work on doing hourly type analysis, 8760 type modeling using a model called ProMod. And the example I'm showing here is an example of the type of results you can get if you're doing hourly power flow. In the past, planners have been looking at time snapshots to really determine what time frames where they might need to focus on either low load conditions or high load conditions, or conditions that the system may not be able to support. And I think as the system operations become more dynamic and you start having backflow from variable resources, you start to get a lot of more challenging conditions. So it's nice to have hourly tools to look at that, not for everything, but where it's appropriate. So in this example, we're looking at, after a series of changes or perhaps addition of generation, you see the red line of the forecast showing significant overloads during the summer months. And what we were trying to do in this particular example is to try to characterize what would a battery storage unit have to do to mitigate those overloads. So in that pop-out box, you see an example of like what one of those overloads on a particular day may look like, because we're trying to search for the magnitude and timing of the overloads and how much energy it would take to mitigate that, so we can compare how a traditional wires upgrade might address that problem, or how a solution like a battery might address that problem. So this is kind of the forefront of the tools we've been developing since the beginning. The other thing we've been doing is non-traditional solution, or NTS screening for storage, where we've been looking at the company's compliance plans and the projects that they have planned, and screening those projects to see if there are any early opportunities to examine storage as an alternative to a wired solution. So that's our initial focus in transmission. Some of the other areas we're exploring now, one is solar and wind viability mapping. mean, this is a subject we could talk about for an hour and a half just on its own, but we understand that we have a lot of information on projects that have already been submitted for review in our interconnection queue, but going forward, we're talking about adding multiple gigawatts of additional renewable resources and starting to explore wind as well. And we don't have as much information in the queue going out in time as far as we need to go. So we're starting to explore some GIS mapping capabilities to tell us which areas of the grid might be the most resource rich and viable areas for future exploration. And that gives us a way of beginning to look at the grid and to see if there are areas that are more amenable to grid redevelopment or upgrades that could help accommodate that. Some of this work has been used to support some of the work that we've submitted in the carbon plan. But there's still a ways to go. We really haven't fully implemented this. So this is one of our exploratory efforts. We're also helping address storage siting on the transmission system and using the valuation approach that we've talked about to look at battery stack values for either for use as a bulk system battery as an energy resource and or for use as a transmission resource to help support the grid reliability. And so a lot of this work is being done. You see evidence of it, early evidence of it in the carbon plan, but there's a lot still yet to be done. And I think the FERC long-term planning NOPR that was released helps outline some of their aspirational goals that transmission planning develop in such a way to look further out and to really begin to address a more robust mix of resources in the future. But I feel like it's early days in this type of work, and so we are learning as we go. The last thing I wanted to mention was climate risk and resilience. We've undertaken a study to examine our transmission and distribution systems to look at climate risk and resilience and see what changes that we might be able to anticipate or to measure going forward in the future, and how they might ultimately impact the capability of our delivery system. Some of those things are, related to storms and flooding and the frequency of storm events. It also relates to trends in temperature because, for example, transmission systems are very temperature sensitive. The ratings of conductors, ratings of transformers. So if you see a trend of temperatures rising over time, that may impact us at some point. So we're starting to put a framework around that and to assess that. All right, I'll keep going. I know I'm trying to cover a lot of material. So the next area I wanted to talk about is our approach in distribution. We have undertaken quite a bit of work in modernizing our distribution planning tools and working with our capacity planning team to help adopt these new tools. We've invested a lot into the grid system data, as I mentioned, in transmission. Even more important, I'd say, in distribution because of the type of data you need to do this very detailed modeling that we might not have had before. We've invested a lot into what we call the ISOP data system, which is a data system where we start pulling a lot of this information together and help create a warehouse of data that can be used by these various models to either deposit information or to withdraw for modeling. So that's been built to meet our needs. We've implemented a hourly circuit level forecast, which our team calls Morecast, where we can get our hourly forecast for each of the circuits on the system, and we can also examine propensity on those circuits for the addition of net metered solar over the future, electric vehicles, and also to start to layer in customer programs, current programs and future programs. So a lot of work has gone into that, and the matching modeling tool for power flow is Advanced Distribution Planning, or ADP. We've used underlying that. We've used some components from SIME that we've built on And so we're able to use that information to do hourly power flow modeling where we need to. Again, we don't need to do this everywhere for everything, but there are certain applications where this really makes a lot of sense. And one of them is looking at how batteries may be able to perform grid functions on the system. So the example I'm showing here is an example of a battery modeling module that we have that we're using, and this module helps you look at forecast overloads on the system and suggest areas on the circuits where a battery might be able to help you. And that allows us to compare that alternative to a traditional solution like a substation upgrade or reconductoring, so forth. So I will also show you the DG guidance map. Sorry, let me back up just in case I missed or advanced the slide. This is the battery location module. This is a distributed guidance map. I know this has been out for a couple of years now, and what we're showing here essentially is a version of hosting capacity on our system, which circuits have the ability to host more distributed generation. So that's posted out on our public site. And the other thing I wanted to show an example of is non-traditional solution screening. This is kind of converting all of those questions for non-traditional solutions into economics that you can actually visualize. And what we've started with is looking at the projects that our capacity planning group is proposing. So as they wrap up their planning cycle, what ISOP has done has come in and taken a look at the list of projects they're proposing and done some screening to try to evaluate whether any of those proposed projects might be amenable to a storage solution. So that's kind of where we started. And we published these results for the planning cycle from last year. So this would have been the planning cycle that started, maybe in August of 2021 and wrapped up in early 2022. And each of these bars that we're showing here is an example of, by looking at those particular applications of those particular traditional projects, this looks at what the battery alternative would look like from a cost standpoint. So the blue bars are the estimated cost of the battery, and this is pretty high level screening, so it's not accurate really by any sense, but it's intended to help you identify candidates that may be interesting. So the blue bar, dark blue bar, would indicate the cost of the battery, and the bars to the right of it illustrate the stack benefits for what the battery may be able to deliver. So the green and light blue bars are the stack benefits of deferring the traditional project, the value of deferring a traditional project in lieu of a battery. And also we're showing the what I call the proxy values or production cost system savings potential for the battery itself. And then the orange bar is just the difference. And that is, in this case, the orange bar is the gap we'd have to overcome for the project to be cost effective. So it helps you kind of take a look at how we're doing this, how we're thinking about stack value, but it also shows you that the projects we're screening in this time frame really aren't clearing yet. So, but we're taking a close look at that, and we hope that over time, as the cost of batteries decline, that we'll see more of these, or some of these, start to make sense. So I just thought that would be a good example to share. Looking ahead, some of the other things that I think have been important for us in our distribution planning practice. One is advanced load research tools for the planners. I mean, they haven't had hourly forecasts to work with before, so we've provided them. And what we find is that, coupled with the automation, Gus described this too, is doing more automation around the forecasting and planning process gives the planners more time to actually plan, to do what they need to do. And so once we get to that point, there's also an interest in starting to look at different scenarios and providing different types of load research, whether historical load research, load shape research, or looking at the forecast and breaking it down. So as we start to put this into practice, I think what we find is that there's an interest in more tools that to go with that to help the planners become more efficient and to explore the possibilities. So we do work on that with them quite a bit. There's also a team working on grid hosting capacity. I think the grid hosting capacity that Dominion performs is more robust than what we've had in the past, and more robust than the DG guidance map. And we're working towards, we've reached some commitments to deliver that in the next year or two. And so we are working on developing the grid hosting capacity mapping systems that folks are looking for. And we're using a lot of these new tools that we've talked about to get there. We're also continuing to refine our approach to battery system stack benefits. That includes branching out from just looking at overload conditions to starting to look at system reliability needs, microgrids, load pockets, things like that. We're also branching out into looking at how to screen customer programs as non-traditional solutions, and those are pretty complex. Most of the customer programs these days are complicated, and they're hybrid programs, and so we're working with the customer programs teams to address how to approach that. And last but not least, addressing climate risk and resilience in this area in the distribution system as well. And so I hope that this gives you a good sense of, going back to the beginning, it gives you a good sense of how we're looking across the enterprise, how we're working with each of these teams to try to modernize the planning approach we're taking, and how some of these results are delivered in various of these public forums, like the IRPs and grid improvement plans and so forth. So I think that concludes my remarks. There is a slide here I mentioned if you have questions afterwards, or you're interested in the portal where you can find that screening tool, or prior ISOP stakeholder work is there, and also the climate risk and resilience portal if you're interested in that work. So I think I'll stop there and turn it back over to David.
Okay, Mike, thank you. That was a lot of information. I do appreciate that. That was very good. Appreciate it all. Okay, hang on. There we go. Okay, so that leads us now to our question and answer session and concludes our presentation. So we'll take a few minutes to ask some questions that came in during the webinar or were submitted beforehand. And please understand we may not have time today to answer all of them. If there's any questions that came up that we don't get to, we'll try to respond to them after the webinar following this presentation. So some of the questions that came in, and I'll start with Gus first. Regarding non-traditional solutions, and then Mike, you can follow on. I heard you both mention non-traditional or non-wires alternatives. Can you tell us a little bit more about what some of those might be and how they're being applied? So Gus, we'll start with you.
Sure. So not like I mentioned, during my time, not a non-wires alternatives or a non-traditional solution, I kind of think of them as being the same thing, are utilization of any measure of any manner of distributed energy resources to either supplement or completely supplant or defer the investment, in a traditional solution. So, several of the battery energy storage pilots that we have going on in Virginia right now deals with just that. So I'll describe two of them that we have in the ground and they're active right now. So one of them is testing the ability of a battery to offload a transformer or to deload a transformer. So we picked a transformer that we looked at and we saw that it was going to overload at some point in the next 5 to 10 years and thought this might be a good candidate. So essentially what we're going to do is set the programming for that battery to discharge when we hit what we're calling a pseudo limit. So it's not the limit of the transformer itself, because we don't want to be testing, when the transformer's at max capacity, but we set a limit to say, hey, battery, once you hit this limit, please discharge and pull the load off of the transformer by feeding the load itself. So that's what we're looking at right now. Another version of a non-wires type alternative is the reduction of backfeeding on a transformer, which is another one of our energy storage pilots, where we have a 20 megawatt solar facility on a distribution circuit that feeds back into a substation. Depending on the right set of conditions, that solar power can then be backfeeding onto the transmission system. And we are utilizing the energy storage kind of in an opposite capacity to see whether we can absorb that energy rather than backfeeding it onto the system. So essentially, once it hits that zero threshold and we're pushing back onto the system, that battery energy storage system would then charge, and it will be charging off of the solar plant, again, to prevent the backfeeding onto the system. But non-wires alternatives really expands, much further than that. We're not doing it currently, but there are applications with demand response in terms of thermostats and utilization of rooftop type systems to really help support the distribution system. Another thing that we will be looking at once we get our DERM system in place is, how can we utilize these energy store or these distributed energy resources for reactive power support, and how can we coordinate all of it, because you got a bunch of different things coming from different directions now, so you really need that DERM system or some sort of control system in place to orchestrate all of it. I could go on and on about non-wires alternatives all day, but just to kind of give you a flavor for it, those are the things that we're looking at, but that is certainly not the limit, and that was not a comprehensive view of non-wires alternatives.
Okay, great. And Mike, we'll turn it over to you.
Thank you. Yeah, Gus, I think you really covered it well. I think using the moniker non-traditional, I think just suggests that, we're looking beyond what capacity planners have traditionally looked at as alternatives. And by calling them non-wires, I think they might be non-wires, but they might not be. So I think the battery storage opportunities are a great example. And I'll echo what Gus said about the fact that what we will need ultimately for this to work will be a lot more visibility of what the resources on the distribution system are doing, because that used to be kind of the last mile or the last couple of miles, and you just assumed it got there. Now I think with the fact that there are dynamic resources and two-way power flow, we need more visibility and awareness of what's happening at that out at that point on the system. And if you're installing microgrids or batteries to help improve the performance or reliability of the system out there, they have to have a mission and they have to be controlled. So we're not really thinking of these solutions as necessarily just uncontrolled resources out there. We're thinking about how would we have visibility, awareness, and control to be able to make sure that they perform the functions that they need to when they need to. So very challenging, and to put the analytics around that's the challenge we have. Try to look at that performance as well as the cost and cost benefit.
Okay, great, Mike. Appreciate that. Another question that came in, and Mike, you had mentioned this in your presentation, but I wanted to drill down a little bit deeper into the climate risk and resilience. What are some specific options that you're looking at in that area, and how are you doing that analysis?
Yeah, I know I'm not the company expert on climate risk and resilience, unfortunately, so I hope I don't miss the most important things. I think what we're trying to look at is to really address what are the challenges ahead as a result of climate risk. So that's the first part. And then the second part, which is somewhat climate related, but somewhat just related to the nature of the change on our system, is how do we address resilience on our system, and what does that mean? So the challenge is to have a more resilient system, looking at the challenges in the future, whether they might be weather driven or climate driven, or whether they might just be, as I mentioned, the complexity of the system operating with more devices, more distributed, and more control challenges. So all that comes together. On the climate risk side, I mean, they are looking at trends and trying to develop credible, supported information about the future trends we expect in weather and temperatures, operating temperatures. And so I mentioned those. Our company has already undertaken some climate risk and resilience related work where we're building flood protection around substations and things like that. We'll be addressing, what's the appropriate base elevation for substations or power generating units, to address flood risk in the future. So trying to, the good news, although these events are coming more frequently, even now, but the good news is that we have some time, as we see things evolving over time, we have some time to respond and react. But if we believe that our systems are more vulnerable in the future, then we know systems that are already on the ground today may have vulnerabilities we need to address. And then for anything that we're adding or new to the system, it gives us an opportunity to look at that and see if we can build in some more insurance. So I'll pause there.
Great. And Gus, could you share anything about what Dominion's doing around that area?
Yeah, so all of that Mike said, is certainly something that, we are reviewing, we are evaluating. I will add a few additional notes in there from our grid modernization efforts. When it comes to resilience, things like our main feeder hardening program, I think is really important. So for those who are unfamiliar with that, essentially what we're doing is we've beefed up our hardening standards, and we are selectively going through and replacing infrastructure on feeders to hopefully, when we have something like a tree fall over on a line, instead of it taking out the entire pole, which leads to longer restoration, and I think everyone's aware of that, it would do things like, break the insulator, break the cross arm, which is a much easier restoration and a much quicker restoration than breaking the pole itself. So we're doing things to make our system more resilient. The outages are going to happen, trees are going to fall. I think the quickness with which we can recover from those situations will help our system be more resilient, and that's a really big thing for our main feeder hardening efforts. I think this also underscores both from a resilience and then also from a climate change perspective and the impact that it has on our assets. This underscores the need for us to continue with our deployment with our enterprise asset management system. Again, this was something that was approved in Virginia as part of our grid modernization efforts. It just gives us more data, more information on our assets, how they are performing in different areas of our service territory, because you're going to have different climates, different environments. Assets are just going to naturally perform in a different manner. And this helps with our transition from a time-based maintenance to really a data-based, a condition-based maintenance sort of perspective for our assets. So instead of just going and inspecting and potentially maintaining or replacing things on a cycle, now we know more about how our assets are living and breathing and their health of them. And it can tell us, hey, you may be on a 10-year cycle for this, but given weather impacts and how the climate is in that area, you either need to maintain it or replace it sooner, or you may be able to stretch out that maintenance cycle a little bit, which, again, gives us more intelligence on our assets. It also could lead to significant cost savings for our ratepayers, and the impact that they feel from us, just maintaining our system. So yes, we're looking at all of that. It is weaved, resiliency, reliability, all that stuff is weaved into all of our grid modernization efforts and a lot of the things that we're doing nowadays.
Okay, well, thank you very much, Gus. We appreciate that. You should see a in your Q&A window, you should see a link to a survey. We want to encourage everybody to please take a moment and fill out that survey. Respecting everyone's time, that's really all the time we have for questions today. Like I said, we will try to respond to any other questions that came in during the webinar that we may not have gotten to. But before we close, first we want to extend our appreciation to all our stakeholders, the many people from Duke Energy, Dominion, North Carolina's electric cooperatives, and the public staff of the North Carolina Utilities Commission, the Department of Environmental Quality, and others who provide input and guidance to make this program a success. And especially want to thank our guest speakers, Gus Johnson and Mike Ribb. We appreciate your presentations. I want to remind everybody to visit the NC Clean Energy Transition website at ncenergytransition.org, where you'll find recordings of all our past Smart Grid Series webinars, and a recording of this one will be posted in a few days. So please don't forget to fill out the customer participant satisfaction survey. We really do value your input from that. Help us improve by filling out that survey so we can continue to offer valuable information and resources for you. So we're grateful you took time out of your day for joining this webinar. Please have a great rest of the day, and we hope to see you in a future webinar. Thank you very much, and thank you, Gus and Mike.